Good morning, Ma'am. My name is Charity Y. Anyana, and this is my report. It's all about architecture and organization. Lesson 1. Digital computers. A digital computer is a system that performs various computational tasks from the word digital. It implies that the information in the computer is represented by the variables that take a limited number of discrete values. It is used the binary system in which has two digits, the 0 and 1. The computer system is sometimes subdivided into two functional entities, the hardware and the software. The hardware of the computer consists of all the electronic components and mechanical devices that comprise the physical entity of the device. And second is the software. The software of the computer consists of the instructions and data that the computer manipulates to perform various data processing tasks. And there are three major parts of the hardware computer. First is central processing unit. Second is random access memory. Third is input and output processor. Computer organization. Computer organization is concerned with the way the hardware components operate and the way they are connected together to form the computer system. Computer design. It concerned with the hardware design of the computer. The computer's specifications are formulated. It is the task of the designer to develop hardware for the system. Computer design is concerned with the determination of what hardware should be used and how the parts should be connected. And computer architecture is concerned with the structure and behavior of the computer as seen by the user. It includes the information formats, the instruction set, and the techniques for addressing memory. The architectural design of a computer system is concerned with the specifications of the various functions, modules such as processors and memories, and structuring them together into a computer system. Now, let's move on in lesson 2, the logic gates. A logic gate is a device that performs a Boolean function, a logical operation performed on one or more binary inputs that produce a single binary output. So, signals, a binary information is represented in the digital computers by physical quantities. Electric signal, such as voltage, exists throughout the computer in either one of two recognizable states. The gates. The manipulation of binary information is done by the logic circuits. The gates are blocks of the hardware that produce signals of binary 1 or 0 when the input logic requirements are satisfied. Truth table. The truth table, the input-output relationship of the binary variables for each gate can be represented in a tabular form. First is AND gate. It produces the AND logic function that the output is 1 if input A and B are both equal to 1. Otherwise, the output is 0. Second is OR gate. It is produced the inclusive OR function that is the output is 1 if input A or input B or both inputs are 1. Otherwise, the output is 0. Second is inverter circuit. Inverts the logic sense of the binary signal. It produces the NOT or complement function. Buffer circuit does not produce any particular logic function since the binary value of the output is the same as the binary value of the input. The NAND function, the complement of the AND function, which consists of an AND graphic symbols followed by the small circle. Exclusive OR gate. The output of this gate is 1 if any input is 1 but excludes the combination when both inputs are 1. Exclusive NOR gate, the complement of the exclusive OR. So this is table of the digital logic gates. And now, let's go to the lesson 3, the Boolean algebra. Boolean algebra, an algebra that deals with the binary variables, a logic operation, Boolean function, and expressed algebraically with the binary variables, the logic operation symbols, parentheses, and equal sign. Complement of a function, the complement of a function if when expressed in a truth table is obtained by interchanging 1 is and zeros in the values of f in the truth table. So this is the example of complement of a function. F equals EB plus C naught plus D plus not B D. Not F close parenthesis not A plus not B open and close parenthesis C plus D and open and close parenthesis B plus not D. So this is the lesson 3. It's all about Boolean algebra. And lesson 4, it's all about map simplification. Karnaugh map or key map, a method may regarded as a pictorial arrangement of the truth table which allows an easy interpretation for choosing the minimum number of terms needed to express the function algebraically. Min term, combination of each variables in a truth table, maps for 2 to 3 and 4 variables function. Product of sum simplification. The product terms are and terms and the sum denotes of these terms. And this is the logic diagrams with NAND or NOR gates. Don't care conditions. The ones and zeros in the map represent the minterm that make the function equal to 1 or 0. There are occasions when it does not matter if the function produces 0 or 1 for a given minterm. Since the function may be either 0 or 1, we see that we don't care what the function output is to be for this minterm. Minterms that may produce either 0 or 1 for the function are said to be don't care conditions and are marked with an X in the map. These don't care conditions can be used to provide further simplification of the algebraic expression. In lesson 5, it's all about combinational circuits. A connected arrangement of logic gates with a set of inputs and outputs. Block diagram of a combinational circuit. The ability to correlate a truth table or a set of Boolean function. And there are 5 procedures. First is the problem is stated. Second, the input and output variables are assigned letter symbols. Third is the truth table that defines the relationship between inputs and output. Fourth, the simplified Boolean function for each output are obtained. And the last is the logic diagram is drawn. Half other is a combinational circuit that performs the arithmetic addition of 2 bits. Full adder performs the addition of 3 bits, 2 significant bits and a previous carry. And this is the truth table of the adder. And the last lesson is flip-flops. Flip-flop is storage elements employed in clock sequential circuits. Synchronous sequential circuits. It employs signals that affect the storage elements only at discrete instant of time. Synchronization is achieved by a timing device called a clock pulse generator that procedures a periodic train of clock pulses. There are 5 common types of flip-flops. First is SR flip-flop. SR flip-flop has 3 inputs labeled S for seat, R for receipt, and C for clock. It has an output Q, and sometimes the flip-flop has a complement output, which is indicated with a small circle at the other output terminal. Second is the D flip-flop, a slight modification of the SR flip-flop. An SR flip-flop is converted to a D flip-flop by inserting an inverter between S and R and assign the symbol D to the signal's input. The D input is the sample during the occurrence of a clock transformation from 0 to 1 if D equals 1. The output of the flip-flop goes to the 1 state, but if D equals 0, the output of the flip-flop goes to the 0 state. The third is the GK flip-flop, a refinement of the SR flip-flop in that the indeterminate condition of the SR type is defined in the GK type. And the fourth is the T flip-flop, obtained from a GK type when inputs G and K are connected to provide the signal input designed by the T. The flip-flop has only 2 conditions. And the last is edge-triggered flip-flops. Output transition occur at a specific level of the clock pulse. When the pulse input level exceeds this threshold level, the inputs are locked out so that the flip-flop is unresponsive to further changes in inputs until the clock pulse returns to 0 and other pulse occurs.